Have you ever just stopped and wondered why everything holds together? Why the universe is so incredibly stable and doesn't just flicker and dissolve into a mess of static? It seems like such an obvious thing, but the real reason why is one of the deepest, most mind-bending secrets in all of physics. Our everyday intuition gives us basically two ways to protect information. You can write a message in the sand, where it's fragile, right? The slightest wave and it's gone. Or you can carve that same message into stone, making it permanent by shielding it from pretty much anything. That's the classical way we think. You either build a fortress around your information, or you just make a whole bunch of backup copies. And that's the big puzzle, isn't it? Our reality feels so solid, so permanent, just like it's carved in stone. But when you zoom all the way down to the fundamental quantum level, the universe is just buzzing with noise, constant jitters, and random fluctuations. So how on earth does it maintain its structure? How does it all not just fall apart? Well, here's the twist. The answer isn't about building thicker walls or making more copies. The real secret to reality's incredible stability is that it's protected by a code. A secret code that's not written on anything, but is actually woven into the very fabric of space-time itself. Okay, so let's dive into this. To really get our heads around this cosmic code, we first have to understand why all our normal ideas about protecting things completely, utterly fail in the quantum world. You see, physicists ran into three problems that honestly seemed impossible to solve. First step, problem number one, the no-cloning theorem. This is a fundamental law of quantum mechanics, and it's a real killer. It says you simply cannot, under any circumstances, make a perfect copy of an unknown quantum state. So right off the bat, our number one strategy for protecting data, just make a bunch of backups, is completely forbidden by the laws of physics. Okay, so if you can't make copies, maybe you can just check for errors, right? Nope. Problem number two, the act of measuring a quantum state actually destroys it. The moment you look at a quantum bit to see if it's okay, you force it to collapse, wrecking the very information you were trying to save. It's kind of like trying to check if a soap bubble is still there by poking it. It just doesn't work. And the final nail in the coffin, problem number three, the errors themselves are infinitely complicated. See, a classical computer bit is simple. It's either a 0 or a 1. It's right or it's wrong. But a quantum bit, a qubit, can be off by an infinitesimally small amount. It's not just black or white, there's an infinite spectrum of gray. There are literally infinite ways for a qubit to be wrong. So just think about that for a second. That was the situation. How could you ever hope to protect quantum information? You can't copy it, you can't look at it without breaking it, and you can't even perfectly define what a mistake looks like. It really truly seemed like an impossible problem. But then, in 1995, a physicist named Peter Shor came along with a breakthrough that just completely changed the game. He found a way to solve this supposedly impossible puzzle, a kind of miracle of code breaking. Shor's big idea, his core insight, was to just totally rethink the problem. He said, forget about making more copies of the data. That's the wrong way to think. The real solution is to weave the data into a larger, interconnected pattern. You don't try to copy the information, you spread it out. And the magic tool for doing this is a wonderfully weird thing called entanglement. It's this bizarre quantum connection where multiple particles get linked together, sharing a single collective identity. You can't describe one particle on its own anymore. You have to describe all of them at once. The information isn't in any one particle anymore. It actually lives in the relationships and the correlations between them. So here's a super simplified idea of how it works. Let's say instead of storing your information in one qubit, you spread it across 3 entangled ones. Now, to check for an error, you don't look at any of them directly. Instead, you ask these really clever questions like, hey, do qubit 1 and qubit 2 still agree with each other? Or how about 2 and 3? That measurement, they call it the syndrome. It tells you if a flip happened and on which qubit it happened. But here's the brilliant part. It tells you all that without revealing what the underlying data actually is. The original information survives totally untouched, and now you know exactly how to go in and apply the fix. It's genius. Okay, so this is a really cool trick for building quantum computers, right? Well, the truly crucial point here is that this idea is so much bigger than that. It turns out this is the very strategy that the universe itself uses to build a stable reality for all of us. And this brings us to a jaw-dropping discovery from modern physics, something proposed back in 2015. Get ready for this. The very fabric of space-time, the stage on which our entire reality plays out, appears to have the exact mathematical structure of a quantum error-correcting code. So how does this analogy actually work? Well, think of it like this. Our three-dimensional reality, the world we see and touch, is like the protected logical information. It's the final stable message. But that robust 3D world is actually encoded on a fragile lower dimensional surface, a boundary, kind of like how a 3D hologram is projected from a 2D surface. All the physical stuff on that boundary acts like those redundant qubits, storing our reality in their complex, entangled patterns. And what this means is something incredible. Your location in 3D space is actually a measure of how protected you are. An object deep inside this bulk of spacetime is encoded across a massive region of that boundary surface. To destroy that object, you'd have to disturb a huge chunk of the boundary all at once, which is really, really hard to do. In this code, depth is literally a measure of safety and robustness. So what does all this cosmic error correction actually do for us? Well, to put it simply, it's the reason we have a stable universe at all. It's the reason we can have a cosmos where complex structures, like stars and planets and us, can even exist in the first place. This all comes down to a fundamental rule of the game called the threshold theorem, and it's pretty simple. It says that for any system dealing with noise, there is a critical tipping point. If the background error rate is below that level, then error correction can work its magic, and you can build stable, complex things. But if the noise level is above that threshold, chaos always wins. It's game over. Think of it like a phase transition, like water freezing into ice. The only reason we're here, the only reason we're able to observe a universe with consistent laws and things that last, is because the fundamental error rate of our spacetime happens to be below this critical threshold. If our universe were just a tiny bit noisier, no structure could ever survive long enough to become complex. It would all just be static. All right, let's just quickly recap the big ideas here. First, we learned that true, robust protection doesn't come from making perfect copies, but from weaving information into these vast, entangled patterns. Second, we saw this incredible idea that space-time itself seems to be one of these quantum error-correcting codes. And in that code, your depth in space is literally how protected your information is. And finally, all of this adds up to one thing. Our stable reality is only possible because the universe's fundamental error rate is on the right side of that critical line, allowing order to win out over chaos. And all this leaves us with a pretty profound final thought to chew on. We tend to think of error correction as this clever bit of technology that we invented. But maybe we've got it completely backwards. Maybe this fundamental physical process of preserving information against the constant onslaught of noise isn't just something we do, but is, in fact, what we are.